All right, welcome to part 2 of our Module 2 lecture series. In this part, we are going to talk about the normal curve, or the bell-shaped distribution. So, in the previous lecture, I showed you guys a representation, right, of a bar graph, or if we had a histogram, it also could be a histogram. Okay, but relatively speaking, this bar graph or histogram would represent a frequency distribution of a given measured outcome. The normal distribution is basically just a symmetrical distribution, right? A perfectly normal curve would have equal frequencies in a stepwise fashion away from the mean, going both above and below. So in this bell curve, or in this normal curve, we would expect the mean, the median, and the mode, which are all of our measures of central tendency, to be equal to each other. Okay, so the frequencies of the scores are going to deviate from the mean in a predictable pattern. The actual standard deviation might be, various values depending on what you're measuring, but it should be predictable in terms of how the deviation works above and below. Okay. So why do we want data to be normally distributed? The normal distribution, similar to random sampling, is an assumption that's used for all parametric statistical tests. Okay, so when you have ratio or interval data, you have to meet the assumption that you have normally distributed data in order for the results of your tests to be actually accepted and interpreted for what they are. What shape do we assume a population sampling distribution looks like? Normal distribution, right? So if we collect a sample, and if that sample is truly representative of the population, the sample distribution shape should be similar to that of the population distribution shape. So that's why we also want a normal distribution for our sample, because that would be representative of what the population distribution would look like. Okay, statistical inference, we talked about it last week a little bit. We're going to talk about it this week a little bit, and it's simply, right, looking at how generalizable are your results. The more similar our distribution is, or the more similar our sample distribution is to the population distribution, the better our statistical inference is going to be on how a particular intervention might work on a certain group of people. We'll talk about that even more next week. But the last question that we can ask to kind of answer this question is which measures are presented in the distribution, right? And that's our mean and standard deviation. Okay, so remember that the mean is really sensitive to extreme scores. So if we don't have normally distributed data, the mean is going to shift towards that extreme score. Okay, and standard deviation, we also know, could be influenced by extreme scores because we're taking the difference between a raw score and the mean and then adding up, right? Or we square, add all of those up, divide by your sample size minus 1, that type of thing. But in both of these most commonly used measures, right, of both central tendency and variability, they are the most sensitive to extreme scores. So if we have extreme scores, we might not have a normal distribution. So it's important that we have a normal distribution to make sure that our statistical tests run nice and smoothly. As a side note, I wanted to talk about something called the central limit theorem. This states that if a sample is large enough, the sampling distribution of a parameter will be normally distributed. Okay, remember that we reference parameter to population. Okay, so if our sample has enough people in it, when we put that sample, right, or let's say we take a bunch of samples, and we plot all of those samples on a single distribution, the shape of those sample means plotted on that single distribution should be representative of our population. Okay, so usually once you get to a big enough number in your sample, it should be more or less what your population should look like. It doesn't matter if you add more people, your distribution should still assume a normal shape. The actual population may not be normal though, so that's something to consider. We usually assume that it is, which is why we take that assumption on for our statistical tests. But when you take an accumulation of your means, again, from randomly selected samples, that distribution should be normal. Okay, so you might not always think that your population is normal, but the sampling distribution of your population should be normal, which is what we're actually comparing when we look at samples. Okay, does your samples distribution look like the sampling distribution, which is a bunch of randomly selected samples, and their means plotted on a regular distribution? A sample that is large enough is usually determined by running a power analysis, which can be run in tandem with a sample size analysis. Large samples are assumed to be about 30 to 40 subjects. Again, you should probably check this based on the variables you're working with to actually make sure that you've met power. Samples that are not large enough may not need normality testing. So if you've got 30 to 40 subjects, you can relatively assume, based on the central limit theorem, that you likely have a normal distribution. It's always good to check your values anyways, just in case you have an outlier. Maybe you can identify a value that was input incorrectly. But usually if you have enough people, normality isn't really a concern anymore because it should naturally happen. When we're talking about the normal curve, we also have to acknowledge the empirical rule. We saw this curve in our previous portion of this lecture series, but the empirical rule is also called the 68, 95, 99.7 rule, which is a little bit tedious to say. But basically, if you look at this distribution, where 0 is the mean, and then we have +1, +2, +3, and -1, -2, -3 standard deviations from the mean. As you move outwards, between one standard deviation, right, plus or minus 1, we should have about 68% of our data included in that region under the curve. So if we took our frequencies that exist between plus and -1 standard deviations, divided that value by our total sample size, it should be close to about 68%. If we look between plus and -2 standard deviations from the mean, we should have about 95% of our data within that region. And then between plus and -3 standard deviations, we should see about 99.7% of our data. Being outside of plus or -3 standard deviations is very rare. Usually if you have a value that exists in these regions, that would be an outlier. Okay. But you can also look at this by adding up the percentages in each of these regions. So maybe you wanted to know what percentage of, if we have a normal distribution, right, what percentage of individuals would lie 2 standard deviations below the mean. You could add up 13.59 and 34.13 to figure out how many people or what percentage of your scores would exist within -2 standard deviations from the mean. Maybe you wanted to know what percentage of individuals lie between -1 and +2 standard deviations from the mean. Again, you add up the percentages, and that relatively is the number or amount of people in your sample that exists between those 2 standard deviations. This is very similar to how percentiles are calculated, right? So looking at or below a given value tells us what percentage of people in our distribution have a given score or below that score. So I've kind of been commenting on percentages as an area under the curve. We can also refer to values under the curve as a decimal, so a non-percentage value, right? And that decimal number can be anywhere between 0 and 1, similar to percentages which exist between 0 and 100%. and that would express the probability or the likelihood of obtaining a given value or raw score in the distribution given certain bits of information. And those certain bits of information will be the mean, the standard deviation, and the sample size. We can use these 3 bits, right, to say at a given raw score, whatever exists at -1, we compare that to the mean, or the distance from the mean, right, divide by our standard deviation, and we should get the probability that that raw score exists at or below, right, in the distribution. So the area under the curve is very similar to the percentage that we would get if we added all of these up, given that we have a normal distribution, of course. Similarly, we could find how many people exist above a certain value. Okay, so the probability that we are at or above whatever raw score exists at this red line. We can also look at values that exist between. Okay, so I gave you guys examples in the previous slide. Again, the method is basically if you have a normal distribution, you can add up these existing percentages that you know of. But if we've got like this 2.5 situation going on here, a better way that we can estimate the area under the curve, or the probability that a score exists between, above, or below certain regions, is using z-scores.